Hello again. Section 5.2 is about the invertibility of some functions. So we'll start by reminding ourselves about some function definitions. A relation is a function if every input has a unique output. And we illustrate this using a table. So like we could have, maybe not a table, but a diagram. We'll have a box for input, a box for output. We can have 1, 2, 3, 4, and say A, B, C, D. And if my function is f, then what I can have is I can have 1 to A, 2 to C, 4 to B, and 3 to D. Or I could even, have 3 to A. The point is that for every number on the left, if I plug it into the function, I can only get one thing on the right. What's not allowed, so we'll say not a function, make this one smaller, 1, 2, 3, A, B, C, we'll call this one G. What's not allowed is to have one number going to two places. So G is not a function because 1 has two outputs. Graphically, what we have for functions is f of x, or a curve, I should say. Maybe I won't use function notations to start with. A graph represents a function if and only if it passes a vertical line test. And what that says is if you have a curve, then no matter where you place a vertical line, it can only touch the curve once. So we'll have a yes and a no picture. This one passes because no matter where I put a vertical line, it's only going to cross the curve once. On the other hand, this one is no good because if I place a vertical line in the right spot, it actually crosses the curve more than once. And so what this is saying is that this x value has 3 y values associated with it. And that's bad for the function definition. Now the reason we bring this up is because we have different types of functions. We could call a function onto, in fact, if it hits everything. So, for example, a line is onto because you can plug in every real number, and as a result, you can actually get every real number. But another one we care about it a little bit more actually in this class. You don't care about an onto property until you get to, oh man, we'll just say senior level math, way at the top. So the one-to-one property, you just use 1-1. We can also say injective. We probably won't ever see that word again. But a function is 1-to-1. Let's say that f of x is 1-to-1 if f of x Oh, let's not use x, actually. I'm going to use a and b. F of a equal to f of b implies a equals b. This is one of several definitions, actually. It's not exactly the one in the book. The one they have in the book has writes this in an opposite order. They use inequalities instead. But what it's saying is that for every y output, there is a unique x. For input. So if I know that my function is equal to 5 somewhere, then I know that there is exactly one x value which is going to give me a 5. As a point of comparison, these are functions that you can kind of think of them as functions that have exactly one root. Compared to the function definition, this is backwards, because of the function definition we have for every x there's a unique y. For every input there's a unique output. But what this is saying is that for every output we actually have a unique input. This also passes a test, so we'll say f of x is 1 to 1 if it passes a horizontal line test. Let's do this actually. So this is a function, it passes a vertical line test, but it's also 1 to 1 because it passes a horizontal line test. No matter which y value I pick, I'm only able to find one x value that associates with it. Compare this to one of our favorites, the parabola. This function is not 1 to 1 because for every x value, for every y value, there's a left side and a right side that I can find x values for it. Now, why we care about 1 to 1 is it's a necessary condition for invertibility. So let's do that definition. Let's see. F of x is invertible if there exists a function, we're going to call it g of x for now, such that f of g of x equals x and g of f of x equals x. So what this is saying is that a function is invertible if I can compose it with something else that essentially cancels it. Strictly speaking, if I have a function f of x, then the inverse, so f of x will take x and give me a y. The inverse will be some other function, we'll say g of y, that takes those y's and gives me the original x's back. So when we're writing x's, we're really just kind of filling in a blank spot. But an inverse, we should consider it as taking the y and giving back the x we started with our original function. And I want to emphasize this right here because people always seem to forget about it. This right here is the primary test. In fact, it's the only test to see if your function is invertible. You have to check both compositions because there are examples where one of these two can fail. And so the function would not be the inverse. Now, something that goes along with this is since this needs to be a function, this is saying that the original f of x needs to be 1 to 1. So if the original f of x is a function, that means for each of my x's, I get a single y as output. Now if I go backwards in the inverse direction and I start with the y's, in order for that to be a function, every y has to have a unique x associated with it, which is exactly the definition of one-to-one. So another thing we can say here is f of x is invertible if it is one-to-one. If f of x is not one-to-one, then when I try to find an inverse function, what I get actually won't be a function because it will fail the horizontal line test for the regular function, which means when I swap the x's and y's, it'll fail a vertical line test as a result. Now, one of our primary goals for this section is how do we find such a g of x? So let's go ahead and write here. We will write g of x as f inverse f to the negative 1 of x. Now, a little notation concern. These mean different things. The -1 as an exponent is an indicator of an inverse of some kind. When I have it on the outside of parentheses here, I'm looking at the number I get out of the function, and then I find the multiplicative inverse of that. So that would be 1 over f of x. But when I put the -1 on the function label, that means I'm looking at the inverse function and not a number. So let's try a simple function. Let's try f of x equals x cubed plus 1. And what we want to do is test if f of x is one-to-one and therefore invertible. Now I could graph this, but I actually don't have to, because if you remember all the way back up here, nope, too far. The function is one-to-one if f of a equals f of b implies a equals b. So what I'm doing is I'm taking my function and I'm going to plug in a and b. So I'm going to say f of a equals a cubed plus 1, and I'll do f of b, which is equal to b cubed plus 1, and I want to set them equal to each other. What this is saying is if I plug in two different numbers, if it's one-to-one, I should get two different answers. So if I plug in two different numbers and I get the same answer, that would force my two different numbers to actually have originally been the same. So if I subtract 1 from both sides, I'll get a cubed equals b cubed. And then I can cube root both sides. That doesn't actually change anything. So I get a equals b as an answer. So since I assumed my two function outputs were the same, and I ended with a equals b, that means that f of x must be one-to-one. But what we also could have done is just simply graphed it and made sure there weren't any up and down loops or anything. No, what's the term? No turning points in the graph. So since it's one-to-one, that must mean that it has an inverse. So how do we find the inverse? Well, since we're going to be dealing with algebraic things, this is, we'll just say it's a lot easier than it could be, simply because there's a process we can do. And there are basically two steps. And the two steps are actually interchangeable. So we'll start off here. We have y equals x cubed plus 1. So 1 swap x and y. What this step does is it's going to ensure that my answer is going to be a function of x that I can deal with, which if I want to graph them at the same time would be something I want to do. So I've got x equals y cubed plus 1. And then the other step, now when and the other step is we solve for y. So let's look at what we have here. We've got x equals y cubed plus 1. I want to solve for y, so let's get it alone. We've got x minus 1 equals y cubed. We can cube root both sides, and that doesn't do anything strange because the cube root doesn't have any positive or negative problems. So as a result, I get y equals the cube root of x minus 1. So at the end of this work, my answer is f inverse of x is equal to the cube root of x minus 1. This second step that I've listed here is actually the work finding the inverse. The first step is just letting me write it as an f of x. Because if I did step 2 first, let's see. Let's make it green, because why not? We've got y equals x cubed plus 1, and I solve for x. Then I will get the cube root of y minus 1 equals x. So what this is saying is that g of y equal to the cube root of y minus 1 is the inverse of f of x. So really it's the same thing that I have down here, it's just I have y's in place. And this is illustrating the fact that, well, on a regular function you start with x, you go up to a y. If I go in the inverse direction, I start with a y and I go down to an x. So the result of this function of y is going to be an x value, which would be an x value that I plug into f to get that same y. Sometimes this step can be harder than others, but this is the basic process. You do one of these two things first. You solve for the opposite variable and you swap the order of the variables. So you might find it easier to just stick with this process every single time. Swap the x's and y's to make sure your answer is going to be a function of x, and then you solve for the y to get your final answer. Now, how do we know that this is actually going to be an inverse? Well, assuming we did our work correctly, an inverse swaps the direction from x to y into y to x. So I know that this step in green, that's actually taking care of that, but maybe I don't know that I did it correctly. So we want to verify inverses. First, let's do an example of one that goes wrong. It makes sense, let's say if I have y equals x squared, you might be faced with this, and it might make sense to say that the inverse is y equal to square root of x. So let's call this one f of x up here and g of x down here, just so that we know they're different. Because squaring and square roots, they're like inverses of each other, right? If I square root a square, I get the x back. If I square a square root, I get the x back. But there is actually a problem with this, and that's because of this. The square root of x squared is actually equal to the absolute value of x. These also have domain issues. So the domain and range domain of x squared is all real numbers. So I'm just going to use fancy R. And the range is positive numbers. So 0 to infinity. Here on g of x, I have a domain from 0 to infinity, but the range is also from 0 to infinity. If we really think about it, if two things are going to be inverses of each other, then what should happen is their domain and range should get swapped. Because the domain goes with the x's, the range goes with the y's. So my inverse function should swap domain and range because it starts with the y's and then it goes out to the x's instead of the regular function starting with the x's in the domain and going up to the y's in the range. And these don't match up. If I test this, that means I need to take f of g of x, f of g of x, and what is that? That is going to be f of the square root of x, which is the square root of x, not quite, well, parentheses, it's going to be the square root of x squared, and here the square cancels the square root, and I get just x. But what we don't see happening here is that the domain of this is only 0 to infinity. So from this step, it looks like they're going to be inverses, but you always have to check both directions. So I should check g of f of x. This is going to be g of x squared, which is the square root of x squared. And the result of this is actually absolute value of x. Because for f, I can plug in any number, positive or negative. Positive or negative that gets plugged in, I square it, it's going to turn into a positive number. Because when you square negatives, you get positives. And then when you take the square root, you can only get a positive number as a result when it's written there. I mean, technically, there are two square roots. There's the positive one and the negative one. But when we do it, we usually only care about finding the positive one. So this answer is equal to absolute value of x. And since x is not equal to absolute value of x, we say that g of x is not an inverse for f of x. Both of them need to simplify to just being x in the very end. So let's see another one where this process works. Let's say here I've got f of x equal to 3x over x plus 2. This is a style we're going to be sticking with, kind of. A nice rational function. And let's say g of x is equal to negative 2x over x minus 3. And in fact, if you start with this f of x and you do the work to try to find the inverse, you'll end up with this g of x. So that means if you say this is y equal to 3x over x plus 2, and then you swap x and y, and then you solve for y, you're going to end up with something that looks like g of x. So let's verify. We'll have f of x, f of g of x. This is going to be equal to f of, this will be fun, negative 2x over x minus 3. So I'm plugging that in place of x on f. So I'm going to end up with 3 times all of this divided by all of that plus 2. Now what should happen is when I simplify this, everything cancels. So let's see. I'm going to try to keep the fractions as long as possible. So the 3 multiplies up here. I'll have negative 6x over x minus 3. On the denominator half, I'll find a common denominator. So this would be minus 2x plus 2x minus 6 all over the shared common denominator of x minus 3. And now we have a division of fractions, so we multiply by the reciprocal, x minus 3 times, we have x minus 3 all over, let's see, we got minus 2x plus 2x, so those cancel, so I just get minus 6 here in the end. Great, so the x minus 3's will cancel, and the minus 6's will cancel, and in the very end I just have x, which is a good sign. But I need to check the opposite direction as well. So f of x equals 3x over x plus 2, and g of x equals negative 2x over x minus 3. I did f of g, so I should do g of f. I will get g of 3x over x plus 2. I'm hoping this is nicer, but it's probably not. I'll get minus 2 times all of 3x over x plus 2 all over, and let's see, 3x over x plus 2 minus 3. Make sure I did that right. Yeah. And we want to simplify it just like we did before. So I'll get minus 6x on top over x plus 2. And on the very bottom, we get 3x minus 3x minus 6 all over the common denominator of x plus 2. Simplify the fraction, x plus 2 times over, let's see, the same thing happens before. We have 3x minus 3x, so those are gone, leaving me with just minus 6 there. X plus 2's cancel, minus 6's cancel, and I'm left with just x. So since f of g of x was equal to x, and g of f of x was equal to x, I can say that f and g are inverse functions of each other. So let's go ahead and say that. Since f of g of x is equal to x, and g of f of x is equal to x, I can say that g of x is equal to f inverse of x. Whoops. There we go. F inverse of x. Although the mirror is actually true as well. I could say that f of x is equal to g inverse of x. And in fact, the inverse of the inverse is going to be the original function. So if I was going to write, I don't know, how would that look? F inverse of x would just be equal to regular f of x. So the basic premise of inverse functions is regular functions, we go from x to y. Inverse functions, we take our y values and we get original x values back. So that's why when we do this work to find the inverse, we swap the x and the y, but really here I have a y value, I want to find the x value, so I solve for x to find out what it could be. If I get more than one answer, then I know that it fails the horizontal line test, and it would therefore not be an invertible function. The test using g of f of x and f of g of x is the only way to truly verify that you have one function as the inverse of another. So if I ever ask you for that, make sure that you check both of them, otherwise you're only going to be half right, because there are examples there are examples. The easiest is with x squared and square root of x, but you can make more concerning looking ones. You can make functions that look like they could have inverses, but the inverse doesn't work both ways. The result of that is the inverse only gives part of the answer, which is going to be a bit of a big issue in the second class, because when you have trig functions like sine and cosine, those fail horizontal line tests in the most spectacular way because they repeat themselves forever. But we still need to use the inverses for those functions to solve problems. And it requires knowledge of what an inverse is supposed to be and information about the domain and the repetition of those functions in order to find out the actual correct answer instead of whatever the calculator gives. More immediately, though, we covered inverse functions because the next two sections are introducing a pair of functions which are inverses of each other. And that's going to be helpful for solving certain problems that use those functions. One of them is exponentials, which is for solving problems with natural forms of growth or decay, such as radioactivity, population controls, or measuring population growths, or spreads of diseases, as the case may be. And we use logarithms as the inverse functions for those exponent functions in order to manipulate them and solve our problems.